So for the video, my name's Reuben Miller. I'm the product owner, and I wanted to talk about the new feature, which is basically enables you to securely store the device certificates using a HSM. So a HSM is the hardware security module. So such things like TPMs or other kind of like hardware-based stuff. So I wanted to give a bit of like an insight into what is this, because that kind of is fundamental before you even start really talking about the feature. So to start off, I wanted to kind of give a bit of a background to, there's different ways to authenticate something or to do authorization, kind of, authenticate authorization kind of discussions. But basically, how do I communicate to the cloud? I need some way of going, yes, you are that person, or I'm authorized to then access your resources. So previously, before certificates there, everyone is familiar with passwords. So basically have a static kind of username password that you use to connect to something. So generally passwords are a very, very poor form of kind of authorization because A, they're pretty easy to guess, especially if you're talking about IoT devices where you might have a bit of lack of like the number of characters you can store in there, or maybe there might be just some limitations into the connecting. So I think currently, might be limited to 32 characters. So it's very, a little bit limiting, and it's a little bit easier, and people are generally terrible at picking randomized passwords. So it would be some kind of common thing, which is a little bit easier also to crack. But also with passwords, they are exposed every time you connect. So they're used often. So it's because it's a shared secret. Both of those bits need to be in both the client and in the backend somewhere to then do the comparison. Yes, you can do hashing on it and don't have to store the password directly, but still it's a very poor form because generally you need it unhashed on the device to be able to use it to connect. And kind of everyone's kind of favorite topic, yes, they don't expire, which is good and bad depending on who you ask. But generally, from a security point of view, that is terrible. So you basically have this forever password that if that gets stolen, you need to change that password. And it is very hard to then check, did that get stolen? So this is where certificates come in. So certificates by nature are harder to crack, basically because a private key is 10 times longer than your password. But also, it's based on the private key, which is like the secret part of the certificate, that is not shared. So that is not sent to the server. So there's basically no kind of interaction that upon like the usage of the certificates. So there's no point that you're actually sharing your secret. So it's using kind of public key infrastructure and fancy cryptographic kind of operations to basically secure a derivative of the key to then prove you're in ownership of the certificate. Then there is mandated expiration dates on certificates. So it basically enforces security best practices. Yes, people at the beginning of their certificate journey generally set the expiration to 99 years, which is definitely not recommended. But it basically enforces at least something. So it's not a forever password anymore. It has a defined time limit on it that it needs to be renewed. And during the renewal process, generally that's kind of like a second validation. Oh, this device exists. I didn't know it existed before. So it's kind of like a touch point back on kind of the server, so you can reissue and get validation that this device actually is there. And with addition, you can also get kind of like identity verification. So this is kind of part of the internal mechanisms for this, no shared secret stuff, that you can basically ask a user of the certificate to verify something, and then you can basically check against the public certificate whether it really was generated from this private key without sharing the private key itself. So a little bit complicated, but just to summarize, certificates are basically the way to go if you want to secure a system. Only if you can't use certificates, should be using passwords, but only if you have a very good technical reason or limitation that you can't be using certificates. So now that we have our certificate, we go, okay, yes, I'm convinced we should be using certificates for verification. What is a certificate? Like, what is the kind of breakdown of the main components which are interesting for users? So obviously, I don't want to go into the nitty-gritty what the different components or the algorithms involved in the certificates. But from a user's perspective, when you have a certificate, there's generally two components to it. There's a private key. Treat this like the password. Never, ever, ever share it. That should not leave the device, because the moment you leave, like take it from the device and copy it, then you have a copy of this, which you do not want to have, because the more copies you have, the easier it is to expose, or maybe it gets kind of, when you're copying it, someone listens into it, or because if you're not doing a secure copy or something, that it just gets, there's a chance of it being exposed. So it should just be a private piece of information that basically no one apart from the client should be able to access. And it'll look something like, this is in the PEM format. So it will have look like, begin and end blocks. The public certificate, so this is like the counterpart. So this is the publicly freely shareable file that you can share absolutely with everyone, because that kind of contains, that's a derived basically from this private key. And it kind of tells a bit of meta information about the that device which the private key is related to. So meta information being like the common name, who gave me this certificate, and also the validity period. So you can determine when will the certificate expire. So these are the two kind of main components. So in the Thinitch's context, there will be two different files. So there'll be a private key and then a public key, or a public certificate. So this point of the private key, how do I secure my private key? So the golden rule is never share it. What is the best way to contradict, or like to prevent people sharing it, is not to give access to it. So this is where HSMs come in, so it's a physical device. So one example is like this YubiKey, which maybe some people are using for personal authentication at the moment. But it could also be like a TPM module. So I've listed a few here, like a Nitro key. I can give a screenshot of what it is later in the demo. Or like ARM, so it has a trust zone, which is like built into the ARM chips, which you then can access to store kind of your cryptographic keys. So these physical devices are also designed to be like tamper resistant, so it's very, very difficult to get anything out of these devices. But obviously, they're storing the private key, but you still need to be able to use the private key, but it doesn't expose the private key contents. It exposes instead cryptographic functions. So generally they involve some kind of cryptographic stuff like signing. There will be like a true random generator inside, because not only generating the private keys, that also needs to be random enough to be secure, so you can't predict what the random is. So it can't be like a pseudo-random kind of process. So the better, the more kind of randomness you can put into the process, the better. So generally, you'll have these chips that will have a true random number generator. But the signing is there to be used by other components. So if there needs to be a kind of check, hey, prove to me you're in the proximity of your private key, then components can then use the interaction with these HSMs to going, please sign this data I was given by the external server to prove that I'm in contact with the thing holding the private key. So because of this, and because it only exposes functions, nothing ever sees the private key, but obviously the hardware module. But there's no user interface to saying, hey, what is it? So there's absolutely no way people can expose or accidentally expose it, because they don't have access to it. So generally with all of these things, like some of the basic functions, there'll always be a way to like create a private key, because you need to use the true random number generator. Create a signing request, so a certificate signing request. So that's what you need when to get the actual public certificate. So you need some derivative from the private key, translate to a certificate signing request, and that is also public information. So you can freely give that to a server, and then it will give you back a certificate in the end. And what I said before with the signing of the data. So this is part of for example, in the MQT process, when trying to connect to the server, part of the communication is then encrypted, so it's using TLS. And with TLS 1.3, it basically says there's a stage of the handshake where the server was saying, well, you've provided me a public certificate. That's fantastic. I will use that for authorization. But before I do, you need to prove to me you're actually in possession of the private key related to the public certificate. Otherwise, anyone could use this public certificate and, spoof who you are. So in that handshake, it will ask to do a client verification step, where the server will give you like a random bit of data. You then interact with the TBM to saying, please sign this random bit of data for me using the private key. It will read the private key and then generate for you and just give you back the signature. And you send that back to the server, and then the server validates your signature against the public key, or like the public certificate, and goes, yes, everything matches. Fantastic, I can move on. I can trust you that you've proven that you're in ownership of this private key, so you can be trusted. So this goes then onto the actual feature, like what is the bit that Thinedge then now supports? So the HSM topic is quite large. But there's a commonality in between all of the HSMs, is that one of the very widely adopted interfaces is called something called the PKCS11 format. So this is basically a programmatic or a specification for interacting with HSMs in a programmatic way. So there'll be like some kind of like shared, like a library that you can use to then interface with these hardware. So Thinedge supports any PKCS11 compatible HSM. So this includes the TPM2s, Nitro Key HSMs, UB keys to some degree, just because they only half implement the PKCS11 format. But we're compatible with that. So as long as if you're looking for a HSM, pick something which is compatible with the PKCS11 format and make sure you read the docs to confirm that it is compatible, and then you should be fine. So with that, we have a new a package which then can make use of this PKCS11 format. So this is an independent package, so it's not part of the multi-binary setup or multi-core binary setup that we have for all the other Tedge components. This is due to a technical limitation. To use the libraries that use this, you can't be statically compiled. So Thinedge is statically compiled for better kind of compatibility with different operating systems. So we had to make sure that the HP11 server is dynamically compiled. Fancy, in the end, you just need to have that installed, and then you'll be good. We have this in a variety of formats. You can build it from source if you really want, but in Debian RPM, APK, Tarball, and you can also install it via Yocto layer as well. So once you have this package installed, you'll need to kind of like initialize your HSM. So generally, different HSMs will have a different initializing process. So you just have to follow the documentation, and that will then create a private key. And you can, so that's where like using tools like GNU TLS are really good. So the cert tool is great for this, can do the initial kind of setup of your HSM, and then prepare for usage with Thinedge. The other kind of constraint, so to support this, we have, or you must use the inbuilt MQT bridge within Thinedge. So this basically means the default at the moment is that we use Mosquito to communicate with the MQT server of the cloud. But for PKCS11 format, we've had to implement our own bridge, which is within the mapper, which then does the connection to the cloud, so we can utilize then more features like this. In the future, this will be the default, but we've just been very cautious with the migration to there. But this will be happening in the next 6 months, that will change the default from Mosquito to the built-in, because it just gives us more flexibility over the whole process. And also, HTTP proxy support and all those things. It just makes it easier for us to control. And like with any HSM, you'll need the PKCS11 module, which is just like an additional library file that you need to install or have on your system, which then, so it acts like a driver, if you can think of it in that way. So you have a hardware module, generally you need a driver to interact with that hardware module. That's the role of the PKCS11 module. So let's have a look how this looks with a kind of setup without a HSM and then with a HSM. So here in a simplistic, so I've ignored all the other components of ThinEdge. So we're just talking about the mapper because that is the only thing which is then using or interacting with the HSM, because that's the one that connects to the cloud. So up here is the example that we have without a HSM. So the TEDge mapper, up till today, if you're not using a HSM, that will interact directly with the public certificate. So this device certificate that you have needs both the public and the private, because it will be then handling this verify step part of the TLS handshake to prove ownership of having the private key. With a HSM, the story isn't actually that much different. So on the file system, you'll still, exactly like here, have the public certificate. So we haven't changed anything there, because again, public certificate can be freely shared. It's meta information about the connection. There's no kind of vulnerability there if you're sharing that. But instead of the private key being stored on the file system, because if it's on the file system, it can be shared, it now is located within the HSM. So this is within the hardware specific thing. So either, in a YubiKey or some kind of like a chip, bit of silicon on the device, and nothing has access to this. The PKCS11 module can then use the API exposed by the HSM. So, performing, as I said before, like the signing operation, saying, hey, can you please sign this bit of data for me and give me the signature back? So to facilitate this, instead of like the TEDge mapper interacting directly with private key, we're using the TEDge P11 server, which has then created a Unix socket, which we interact with, and that is delegating all of the HSM interactions via the PKCS11 kind of format. So that's hence why it's called P11. That's also a common kind of short form of PKCS11. So this means that the TEDge mapper, we didn't have to change a lot in there, apart from saying, hey, instead of doing the verification within our code, just delegate it to kind of socket calls. But also means we're very flexible in the deployment of this. So this component can remain statically compiled, and it's only this component that needs to be built slightly differently, be dynamically compiled, so it can pull in the required objects. And that's it. So it should be very, very familiar. So if you're still like parsing, I know the public certificate because you want to get the bit of information from it, it's still there exactly where it was before. And if you're using the private key for some kind of unsanctioned thing, you shouldn't have been doing that anyway. So that's the whole point of the HSMs. So, but with the TEDge P11 server, what that actually enables us is to be a little bit flexible with the deployments. So this is showing the same kind of representation, but on a device with, let's say, a HSM installed. So at the bottom here, since the TEDge P11, that has to run on the host, because that basically needs the access to all of the underlying devices on the Linux operating system. That exposes a Unix socket. But because we're exposing a Unix socket, that means we can actually expose it to different kind of components at different kinds of points. So either if it's on the host, it's a Unix socket, or if you're having like ThinEdge, like in the wind farm operator case, you have the TEDge mapper, which is actually running inside a container. So you can mount the Unix socket within the container, and then everything still works as before. So it means that it's very, very flexible, and you can change things, how it's deployed. You could also change your mind. In the end, it's still, you're interacting with a Unix socket, so it doesn't really matter. So when you interact with a Unix socket, that triggers then, a verify operation from the TEDge P11 server. You'll have configured which HSM are you interacting with. So in the HSMs, you generally only have one HSM. Technically, yes, you can have multiple, but it's just configuration. But generally, you'll have one kind of in there. So in the example that I'll show, I actually have something like a YubiKey, so it's a Nitro Key HSM. So it's a USB-based kind of module, but I'll just use the YubiKey for here, demonstrational purposes. So you'll have a piece of hardware. We'll have a mirror module that will be called something like yk-something.so. So it's a shared object library file, which that is then used by TEDge P11 server. So that will then load this, because that is like the driver to saying, well, how do I actually use and translate this PKCS11 format request into the hardware that needs to kind of like actually give me the cryptography, like the execute the cryptographic functions. So it's basically a one-to-one kind of mapping. There'll be a one module per kind of module as a kind of like a rule of thumb, but it kind of depends on the standards that are implemented, but I'll show this shortly. And so once you have all that set up, everything just kind of works as it should, as you would expect for any kind of thing. So let's kind of show this in a little bit more context, because I know a lot of theory there, but let's see how this looks like in practice. So we have, so this is the module, the device. So here I just have a Raspberry Pi 5. So I have a HSM, Nitro key. So it's a USB based. So obviously if you run off with a USB stick, you will have the certificate. But generally it's if you don't have a hardware, soldered on component, then that's the next best thing. So I'm just going to connect because it's a little bit easier to show on the shell. So I'm just going to connect here to using the remote access feature, connecting via the cloud, so I can do all my commands as I would. So I can actually see, how does it look like? So I've already connected and configured everything. How do I tell if it's using a HSM? So I'm going to use the test command. So connect to Comvelocity, but I just want to test the connection. So we've added some output here that kind of gives you clues. Oh, it's using a HSM. So the clue is here, the crypto key. So the crypto key is the another name for the PKCS11 format. But I guess people got sick of saying PKCS11. So the C function is called crypto key. So crypto key is a kind of like a pseudonym for it. So here I can say, or I can tell I'm using a HSM. Cool. But maybe I don't believe that. Let's check and make sure there is actually no private key. So if I look in the folder where normally the private key would be, I don't have a private key. So I'm just using the certificate, again, public information, but the private key is nowhere to see. So where is the private key? So the private key, you can kind of, so most of the PKC11 format will have a whole bunch of like CLI tools that you can use. So you can kind of list the tokens. Again, this is just part of PKC11 format. So, you can read the tutorial about it to get all the terminology correct. But I can basically have a look on the local kind of device, what kind of interfaces do I have available? So here I just did a list tokens, and I can see I have a smart card. That is just how the Nitro key then appears on the system. And this module that I was always talking about, like this kind of library file, this kind of indicates to interact with this bit of hardware, you need to use this pkcs11.so file. So this is the dynamic library that then is actually the API, which is then used by the THP11 server. So that's really just showing where it is and how to use it. But if let's just do a reconnect COI. Everything kind of looks exactly the same. You shouldn't really notice that you're not using a file-based thing, because everything just works exactly how it did before. So it's a really consistent user interface. You can configure it. So if we go crypto key here, crypto key. So I'm using the new filter command on the config list. So you can just give it a partial string and it will only give you those. So I can see that I'm using a socket-based mode. So I'm using a Unix socket to communicate with the THP11 server. I've configured what module to use. So that aligns with the output from the P11 tool. And then generally to interact with these things, you need like a pin. This is really just an API pin. It's not really secret because no one can do anything with it anyway, because you need physical access to the device, or like to software running on the device, which then can access. So I can kind of see it's using a socket. Just out of curiosity, if I wanted to kind of debug if something isn't going right, server.socket. So I can see on a systemd-based system, this is running as a systemd socket. So it would be a socket activated service. So that's a fancy way of saying the server won't start unless someone uses it, which is a really, really convenient function, especially for if you have devices with not a lot of memory. And you can see that it's already triggered the service. And if I wanted to get the status of the service, again, standard systemd CLI tools, that I can see that the socket is running. It's been running for over 3 weeks. And then I can kind of see some incoming requests that every time the FinEdge mapper tries to connect to the cloud, it needs to then use this interface to then do the verify step so it can prove it's in ownership of the private key. So if everything goes right, you should not notice a thing. So it's a one-time configuration that you define where it is, what module it is, and then it's a hands-off approach. So we have an examples within our regex, which if you use, it's the last thing I'll show. So where is it here? If you use like a kind of a more hardware, so not a USB-based thing. So we have an example in our regex for this, if you have the same kind of module, or you can just buy yourself a USB-based thing if you want to explore it, or if you can also use, there's a software-based HSM called Soft HSM 2. You can also use that if you just want to kind of explore the topic a little bit and get familiar with what is it, where is the private key stored, and all this kind of things. But that's more for a testing and in-depth kind of situation. Never use soft HSM within the field or in production because that is not storing your keys in hardware. That's just in a file. So those are the main bits that I wanted to show. I know it's a little bit technical, so probably a little bit hard to follow, but are there any questions?
We'll take one because we're running out of time.
Yeah.
Maybe a question. Ah, Nico?
Yeah. Any thought on the key education?
Your microphone's very low.
Oh, sorry. So there's this this challenge that you do not know whether a device uses the private key from the trusted platform module or any file-based private key, which is addressed to this key attestation. Is there any idea to support that?
Not at this stage, but we're definitely happy. Like it's our beginning introduction to the PKI 11 format. So we've made it technically work, and there's definitely some maybe improvements that we could do to make it, initialize the keys. Can we support that through a attach CLI command and things like that? But generally, a lot of the tooling, if you use cert tool from GNU TLS, that can basically do everything. So we didn't want to, re-implement GNU TLS. So you can still use the public open source CLI tools out there to do the same thing. If there's some kind of missing functionality to do attest stations or whatever.
Thanks.
Okay, if you have additional questions, please take it offline and ask Reuben in the chat or offline.